We are here. We have to do largest prime factor. This time we have to find the largest prime factor of the number is 1. Prime factors of 13,195 are 5, 7, 13, and 29. To really understand this exercise, we have to back it up a little bit with some theory. So my friend, I created this little presentation just to be everyone on the same page and to understand what is a factor, essentially. Well, there is this thing which is called the fundamental theory of arithmetic. Wow, what a mouthful. It basically states that every non-prime positive integer major than 1 can be factorized in one way as a product of prime numbers. All right, these definitions all the time are kind of tricky to grasp, so we shall understand on a practical standpoint what are we saying. So let's take, for example, the number 42, the integer 42. So we are not dealing with real numbers. We are dealing with natural numbers, namely numbers which are positive measured than 1. So 42 is a natural number, and it turns out that it can be decomposed, it can be factorized into prime numbers. In this case, the factors are 2, 3, and 7. So if I multiply 2 per 3 per 7, I get 42. Easy peasy, right? So now let's understand better this idea. First of all, a prime number, by definition, is a whole number, namely an integer greater than 1 that can be divisible only by 1 and itself. You know this stuff super well. On the contrary, composite numbers can be divided also by a value which is different by 1 and itself. That's the difference between prime numbers and composite numbers. I think that a really good mental model to understand primes and composites is to pretend that numbers are like atoms and molecules, right? You can basically perceive every natural number major than 1 an atom or a molecule. Atoms are the prime numbers. They cannot be subdivided. Indeed, atom means not breakable. I cannot cut an atom, right? The word from Greek, tomar. Tomar means cut. So uncuttable, basically, an atom. Composites, on the contrary, are numbers which are composed of atomical parts, namely prime numbers. So primes cannot be decomposed, cannot be factorized. Factorize is a fancy word that means made up of, from Latin facere, made up of, fare, to do, to make, that's the meaning. While composites are built with primes. They are molecules. They are built with prime numbers, which are atoms. I think this is a good way to see what is going on. So let's understand better this idea. Let's take into example 42 still. When I do prime factorization, what I'm actually doing, I am decomposing my molecule, my 42, into its constituents, which we understood now that are primes, right? I can do the same with the water molecule, for example, which is composed of atoms indeed. A molecule of water is composed by 2 hydrogens and 1 oxygen. So when we do prime factorization, what is really going on? Well, I try to get the building blocks of the composite number. And we know from the fundamental theory of arithmetic that every composite number is composed by prime atoms. So I get the division. We start by 2. 2 as a prime number is divisible only by itself and 1. So it's 42 divisible by 2. Yeah, of course it is. So I make the division, 42 divided by 2, I get 21. Cool. The analogy holds with the water molecule. As you can see, I've popped the hydrogen atom. Then I say, is 21 divisible by 2? No, it is not. Namely, it is not clearly divisible. I have a reminder. So I have to divide 21 by 3. Well, 21 is divisible by 3. Okay, so I do the division by 3. I get 7. As well, I pop out another hydrogen atom from the molecule of water. Then I have 7. 7 is a prime number because it doesn't have any divisor different from 1 and 7. So I have to divide 7 by 7 itself, and I get 1. Okay, so now I decomposed my 42 into prime factors. As you can see, 2, 3, and 7 are all prime numbers. 42 is a composite number because I can break it down into its constituents which are prime numbers. As well as I can decompose water molecule into its atoms, 2 hydrogens and 1 oxygen atom. They cannot be further decomposed. They can, but that's another story. Pretend they cannot be further decomposed. Cool. I think this is a good framework to understand what is factorization. What do we mean that a number has some prime factors? Let's try to have a visual understanding that, in my opinion, is the best thing to understand this stuff. Does it mean that 42 can be factorized into some prime numbers? Well, we have to understand that a factor of a number is a different way to divide that number into an equal-sized group. For example, let's understand it visually. So as you can see here, I've depicted 42 as a square made up of 42 units. So I have a 6 per 7 square. So I start my factorization in a visual way this time. So I divide my 42 by 2. Cool. So I divided my square into 2 parts, right? What does it mean that 42 by 2 is equal to 21? Well, it means that I have 21 couples of elements inside of 42, right? I have 21 couples. So I can divide 42 into 21 couples. Then I have 21. 21 is divisible by 3. So I say 21 divided by 3. I'm going to get 7. So I have 7 triplets, right? 7 triplets in which I can divide my 21. Indeed, right? If I multiply 7 per 3, I get 21. Cool. Then at the bottom, I have 7. 7 is a prime number, is not further divisible. So I have 7. Cool. So the prime factors can be visualized like dimensions of a number. It is a neat understanding of what is going on. As you can see, 42 can be composed in 2, 3, and 7. And I can see these factors like dimensions of a rectangle. As you can see, I have here a 3D rectangle with a base 7, height 2, and depth 3. Indeed, the volume of this object is 42 cubed. But anyway, this is the way I like to understand what are factors. I don't know if mathematically it is correct, because I'm not a math teacher. I study by myself, and I always try to find some gimmicks to understand what is going on. And this is a pretty neat understanding, in my opinion, that worked for me. Of course, I pledge you to search by yourself this factor deal. Now, my friend, I pledge you to watch this video from Khan Academy, which is a very cool channel, the fundamental theorem of arithmetic. Super well done. Here, they let you understand what is going on with this factorization, and you can visually appreciate that every number has a specific lock. Basically, every number has a specific pattern of prime numbers that can open, quote unquote, open the number. So factorization is pretty useful when it comes to cryptocurrencies, for example, or cryptography in general. So this is not going to be useless stuff for you. You just learn a very important concept here. Coming back to us, we have to find the largest prime factor of this big number. All right, let's start with C. As usual, open my terminal, CD, desktop, Euler project, make dir problem 3 and CD problem 3. As you can see, my fish shell is amazing because it's prompting me with what I'm gonna do. It already knows what I'm gonna do, so I do that. And then I'm gonna just do vim main.c. As usual, we create our boilerplate of the function, include std io.h, standard input output, and my main function. Cool. First thing first, we are dealing with such a big number, so we have to use a big data type that can contain this value without overflowing. I'm going to import the standard int header file, include std int header file. This file contains a lot of good stuff. Go here to open group, and basically here I can use all these ways of declaring variables, which is pretty neat, pretty elegant, and not too verbose. For example, if I want an unsigned long, look how much I have to type. I can do int 64, okay, type. Unsigned int 64, it's the number of bits, type, so it's 8 bytes. Unsigned, of course, because we are dealing with a positive number. So, and B, I declare my variable. I really like to make the declaration and the assignment of the value in different steps. So I can have a place where I declare all the stuff I need, a place where I give the value to my variables, and a place where I have the algorithm itself. So it's divided into logical chunks that are useful for me. So I need my value, and then I need my divisor. Let's make as well an unsigned int t. So even though it's going to be a little number, divisor, cool. So and b is going to be equal to the big value, okay? I'm going to copy that. I'm going to paste here. Okay, assign the value. Given that the number is odd, I don't have to check for 2 if it is divisible by 2. So I'm going to do divisor equal 3. Okay, so now what I'm going to do, I have to find the largest prime factor of the number. I'm not going to check if the number is prime or not in this first implementation. I'm just going to do a naive code just to get the answer. So basically, my friend, what I'm going to do, I'm just going to implement the visual representation you see here. Basically, this continuous division until I reach the value 1. Okay, so I will start with 2, then 3. I will all the time check if the number is divisible clearly if I have a neat division. So I say while NB is different from 1. So here what do? I say if the number is neatly divisible by the divisor. So if NB modulo divisor equals 0. I don't really like this way of typing stuff. I prefer the bank. So I do bank NB modulo divisor. Basically, I'm going to invert the logic. If NB modulo divisor gets me a 0 reminder, I'm going to invert the 0 to a through. What do you do? Well, you just divide the number, right? You do NB divided equal divisor. Then what do? You just increase the divisor. Now here, there is a little bug. Can you spot it? Basically, I'm not checking if I can divide the number by the same divisor more than one time. For example, let's pretend I have the number 48. If here I had the number 48, I can make a division by 2, I get 24. 24 is still divisible by 2, so I can divide by 2, I get 12, and so forth. I have many divisions by 2, right? So here I have to use while. So I say while I have a neat division, just perform the division. When this is not true anymore, you just increase the divisor. There is another little bug because the divisor is increasing by 1, but I don't want, because I want to jump only with odd numbers. I want to perform the division only with odd numbers. So it's going to be divisor plus equal 2, right? I go 3, 5, 7. I don't care about making the division with even numbers, given that the number is odd. Okay, so here I'm going to exhaust the number until I'm going to reach the value 1. Now, let's printf the solution. So the solution of my riddle is %d, new line, and I put divisor. Here I have to change this one to long unsigned. Okay, and there is another bug, which we're gonna spot later. Okay, let's exit this. So upper ZZ. Okay, we compile the code and then we'll launch it. The solution of my riddle is this one, which is wrong. I'm sure this is wrong because here you see the problem. I have the divisor plus equal 2, but here I can have already the number which is equal to 1. So I don't need anymore to increase divisor by 2. So, or I put divisor minus 2 here, which is not elegant, or I do this. I just make this one 1. And I change the position of this to this position. So before performing the division, I increase the divisor by 2. Cool. So we get rid of this. Okay, let's do again the compilation and let's launch the program. GTC, let's see, a.out. Okay, the solution, of course, is true less, and let's see if it is correct. I'm gonna post check. Okay, it is correct. Congratulations, perfect. Now, this algorithm really sucks because, first of all, it is usable only with this input. Every time I have to go inside the program and change the value if I want to find the largest factor of a number. On the second hand, is not optimized, so it doesn't check if the number is prime or not, and overall is not good. It is highly tailored for the specific task on hand that we have. So we're gonna give some steroids to this algorithm. So let's make this time in C++, okay, just to make it different. But anyway, they are so similar, the languages, which is going to be the same, basically. We just change, as always, the include into IOStream, and we change the include to C stdint to use this type unsigned int 64. Then I have my main function that this time I'm going to change because I want to have a discussion with my shell, with my terminal. To do that, I have to use command line arguments, which are int argument counter, char star argument vector. Okay, here it comes. If you don't have a clue about what is going on, I made an ad hoc video so you can understand better what are these command line arguments. Hopefully I explained in an easy way to understand. But basically, long story short, with these variables, I can have access to the arguments coming from the shell. To make it clear, if I have, for example, a program called foo.out, I can give to this program some inputs, for example, A, B, C, delta, I don't know. These elements are command line arguments. Basically, I can give this variable directly into my program. So it's very handy if I want to have a program that can take very different inputs. The idea is that I want to create a program that is able to take whichever input and spitting out the biggest factor. So main.cpp. Now, first problem. Every command line argument is a string. So I need to take that string and convert it to an integer, to a value. So I'm going to do unsigned int 64 type, or better this time, let's make a signed value. I'm going to handle if the number is negative as an error. Okay, so int 64 type mb declare and int 64 type divisor as before. Now, to get mb, I told you that I have to convert the string coming from the command line into a value. For this, there is this function, which is string to long, comes from the string file, and it works in this way. Here you can see the prototype, basically the API of the function, how to use it. So I have a string, the input that is going to be converted to the value, a pointer that is useful if you want to check if there are some errors. Now I don't need it, so I'm going to set to null. And the base, of course, you can convert the number in whichever base you want, base 2, base 8, base 16, and so forth. Okay, to use it, I have to write in this fashion because it comes from the namespace std. So nb is equal to std colon string to long, okay? The string comes from argv in position 1 because the string in position 0 is the name of the program itself. Then I have null. I don't care about checking if everything is correct. And then I have the base, which is base 10, of course. Cool. With this fancy line, I managed to take the first string coming in the command line and converting to a long value. Now, this time, before doing all my calculations, I want, first of all, to check if the number is a prime. Namely, I cannot decompose the number in atomical parts. So I'm going to do a function which is prime. So I'm going to print in the main function. If the number is prime, then now I'm going to create this function. So the number nb, what do we say? Well, we're going to say std cout. I want to print in the standard output. The number is prime. So I cannot decompose in anything. And then here I can put std and line. Cool. And then we just simply return problem is finished. Or here we can put 1 just to say there was a problem, but the process works properly, just the logic that is flowed. Anyway, you can put whichever number you want. 0 is for correctness of the program. Every other number is some specific problem. Anyway, so if it is prime, get out. I don't care. Then if it is also negative, we are not going to deal with negatives here because of mathematical reasons. Just search for yourself negative factors of a number. So if nb is minor than 0, what do? We say std console out. I don't deal with negative. I don't deal the negatives. Okay. And then std and line. Return true. The contrary, if the number is not prime, so not is prime, okay, and b, what do? And here we're gonna have our algorithm. Now let's implement the is prime function. We're gonna implement just above the main function. So what we're gonna have a boolean is prime with our input, which is unsigned int 64 type and b, or better not unsigned but signed. So here let's just remove this one. Let's just remove this exit condition. So you understood that a prime number is an atom. I cannot decompose it in its constituents prime numbers. It's unbreakable. So to prove that a number is prime, I just have to prove that there are not divisors that neatly divide the value. Now I can brute forcefully try all the numbers, trying to search a divisor. If I found a clear divisor, okay, it is as a divisor, so it's not a prime. But this is silly. I have to search too many values. Now, there is a very cool empirical observation, which is this one. Every composite number, namely every molecule, has at least one prime factor less than or equal the square root of itself. Okay. What does it mean? What are we seeing? What how we can understand this idea. Let's pretend we have 42 as our example. So 42 is a composite number because it is decomposable in prime factors, as you saw. These prime factors are 2, 3, and 7. I can say for ease of comprehension, 6 and 7 are the prime factors, even though 6 is not a prime. Just keep with me, it is just to explain this idea. The square root of 42 is roughly 6.48, right? But what is this square root operation? What is going on when we square root a number? As usual, I propose to you a visual understanding. Here I've drawn the 42 in its 2D representation. So it is a square with a base of 6.48 and a height of 6.48. As you can see, I have 36 squares, which have the value 1. And then I have on the sides 12, 0.5 roughly squares. So the value is going to be roughly 6, right? It's 0.48 per 12 plus 36 plus a little chunk. As you can see, there is a little square on the top right, just to fill the gap. And this is 42. This is the area of this square. Now, when I perform the square root on this value, 42, what is going to happen? Well, look carefully now. I'm just taking the base of the square. I'm taking the root of the square. So every value I can consider it as a square, as a value, as a 2D element. So every value I can consider it like a square. Indeed, the square root. I take the base of that square, which is 6.48. Okay. So when I do the square, what is really happening? When I say 6.48 squared, what is happening? Well, I'm creating literally a square. So you see that I have this toggle effect between the square root and the square. Every time you make a square root of a value, you're taking the base of that 2D object that the value creates. Okay. That's why it is called the square root. Indeed, we're talking about squares. Now, what is the take-home message that I want to give you? Let's reread again the line of before. Every composite number, like 42, has at least one prime factor less than or equal the square root of itself. So that 42 has a square root of 6.48. So why this composite number has forcefully to have a factor which is less or equal the square root of itself, namely 6.48. Let's again watch it visually so we can appreciate this idea. As you can see, here I have two squares. In one, I have a square which is composed of the square roots, namely 6.50 rounded to make it easy, and another square which has 6 per 7. 6 per 7 are the prime factors of the value 42. Now, you know that prime factors are positive integers, right? They are not real numbers. I cannot have a factor which has a floating point. So pay attention to the images now. I have two squares. 6 per 7 is equal to 42. Likewise, 6.50 per 6.50 is equal to 42. The values are the same in a 2D image. Now, when we have a composite value, you know that at least the value can be decomposed into factors, right? Like 42 at least has two values that are multiplied and give rise to the value itself. Otherwise, we are dealing with the prime value, right? A prime is divisible only by 1 and itself. So what is this trade-off that I want to convey you? If I increase by 1 the factor, just by 1, just to make it clear, you see here, I have 6 per 7 is equal to 42. And 6 is less than the square root of the value 42. And it has to be, because if I have 7 per 7, I get a bigger value. I get an overflow. I have a value that is bigger than the one the factors are trying to represent. So if I don't have at least one factor less than or equal the square root of the value itself, I'm sure to get a bigger area. You see here, the constraint is pretty visible. I have 6.50, 6.50, which is the square root of 42. If I want to create the same value, the same square with other values, I can increase by 0.50 the height, but I have to decrease the respective base by 0.5. Otherwise, I will get a bigger number for sure. So you see, there is a trade-off when I have a composite value. I'm sure that one of the factors is always less than or equal the square root of the value itself. Hopefully, with this visual, it's easier to understand. So with 42, I'm sure that one of the factors is less than 6.48 for sure. Otherwise, if I have 2 7s, it's not going to work. Of course, this is a 2D representation, but if I want, I can make also a 3D representation. This is just for ease of comprehension. So let's translate this in code. So let's make the first condition. If NB is minor or equal 1, namely, if it is a negative or if it is 1 or 0, it is not a prime. Or I like to go on the next line, or what? The number is even, because if it is even, of course, it's divisible by 2, so it's not prime. The number is even, so not NB modulo 2, but it has not to be the 2 itself, because 2, it's the only even number which is also prime. So and B different from 2. Okay, so I just group all together to make it crystal clear that it is an expression. Okay, in this case, what do? We return false, right? So if the number is minor or equal 1, or the number is even but not 2, this is not a prime. Okay, on the contrary, if the number is indeed 2, what do? You return true. Okay, these are the conditions. Now at the top, we're gonna make the variables. Do integer divisor, and we do integer square root for the reason we explained just a minute ago. So inside the square root, I'm going to put the square root of NB. So I have to check till the square root. If I don't stumble upon a divisor, it means that the number is prime. So square root NB is gonna give me back a double, so I'm gonna cast into an integer. Okay, in this fashion, get the square root. The divisor, I can start from 3. Then I say while what? While divisor is minor equal the square root. And you're gonna say if the number, so NB modulo divisor equal 0, this time we do like that, you return false, because you stumbled upon a divisor in the range which I'm interested, namely from 3 to the square root of the number. And then we just increase the divisor plus 2, like before, because I want to go from odd to odd divisor. If it's gonna pass all these tests till the square root, I'm gonna return true. Okay, I think this is correct, right? So if the number is minor or equal 1, or the number is even, return false. The number is 2, return true. I can also say the square root floored, the floor square root. I don't want like that. I need to floor because for the same reasons we explained before. Let's pretend we have the number 48 this time. The square root of 48 is 6.92. So I have this square that has 2 values. The prime factors are integer values, so they're not real values. If I have both the factors that are sealed, namely if I take both the values which are 7 and 7, what is going to happen? Well, I get 49. I get 49. So I'm sure that I have to check the floor of the square root. Okay, I think these ideas has to be understood by yourself because it's kind of tricky to explain them. Hopefully I can make some clarity, but I'm not a math teacher myself, so I struggle myself with these ideas. Anyway, I think that this is the is prime function correct. So I check till the floor square root of NB. So here we have to give the value to the divisor, which is gonna be 2, divisor equal 2. Let's say while NB is different from 1. Remember, right? We want to exhaust the composite value until we reach 1. We do if NB modulo divisor, and we invert it. If not NB modulo divisor, namely not if but while, for the same reason as before. I just keep making the same mistake. We divide the number, so NB divided equal divisor, and then like before, I prefer to put plus plus divisor here, and we change the divisor to 1. Okay, so we start divisions from 2. So we have our division algorithm that is brute forcefully searching for the biggest factor. Then I have std console out the biggest factor. The biggest factor of n is space divisor std end line. Allegedly this is correct, so we're gonna compile and then launch with an input which is 42. The biggest factor of n is 7, and indeed it is. We give it a prime number 7. The number is prime, the number is prime, the number is prime. Cool. seems to work. -1, I get an infinite loop because I'm not handling correctly. So we do v minus v main. I should do like that. Here I change. I divide it into 2 blocks, minor equal 1. I do, just to make it easy, std cout wrong input. Okay, wrong input, std end line. And then I'm gonna exit directly. It's not gonna be anymore. Basically, if I have a negative or 0 or 1, just go out and say wrong input. Okay, let's go back. Let's recompile and launch this time with -1, wrong input, or if I have 0, wrong input. So let's try again with a big number from project Euler. So we do head.out, we pass the input. The biggest factor of n is this one, 6857. And of course is the result. So we managed to make an algorithm which is reusable for many numbers, as you can see. It's going to give me back the biggest factor of every number, not negatives. If we want to make it more performant, we can. I prompt you to watch this Siebhoff Era, pronounce this name. This is an algorithm that is the best to search for primes, allegedly. Okay. All right, that's it for this video, my friend. I hope I managed to explain how I approach this problem in the best way possible. I repeat to you, I'm not a math teacher, of course. Print in the comment like you got it bad in this point for this reason, and this is how should be done. It will be useful for me and for everyone watching this video. All right, thank you for watching. Enjoy, my friend. Today is not going to be Python, otherwise the video is going to be 3 hours long.